Good morning, good afternoon, or good night, depending on what time of the day you are listening to me. This is chapter 51 of a book I'm writing. Actually, the second part of a book I have written several years ago. I'm going to speak in English, but my text is in Portuguese, Brazilian Portuguese, and I'm going to talk today about the Debye-Hückel approximation. The purpose of this chapter is to present the Debye-Hückel approximation, and at the end we will be able to calculate the activity coefficient to make some prediction about the activity of some ions in solution. The Debye-Hückel approximation is a theory that involves electromagnetism and statistical mechanics, but very simple framework from these two theories. From electromagnetism, we are going basically to use the Poisson equation for spherical symmetry, and from statistical mechanics, going only to use Boltzmann factor. You may realize that the theory for electrolytes is more complicated than for non-electrolyte systems, since ions in solution they have this Coulomb interaction. They have the Coulomb interaction. And even in gas phase, it's a complicated problem because you have to handle this Coulomb tail. The potential energy is 1 over R of this form. We are going to use T3 prototype systems in aqueous solution. Sodium chloride, sodium sulfate, and the copper sulfate. And these are examples of electrolytes of the kind 1 by 1, 1, 1, 1 by 2, and 2 by 2. This kind of notation is used for this type of electrolytes. In the Debye-Hückel approximation, it's assumed ionic atmosphere that's characterized by something called Debye radius. Of course, this Debye radius will depend on temperature and concentration of the particles. The electrical potential generated by a charge zKa E of this form depends on 1 over R. But since there will be a charge around, let's say a positive charge, this charge cannot be, this charge actually will be blind, it will be shielded by the other electrons. And it is about this shielding, this ionic atmosphere, that is the theory of Debye-Hückel. Debye-Hückel tried to modify this form of the potential by introducing a function f of r that will shield, to blind the other electrons and the central particle. If you may realize, we have dealt with that before in the Hart theory or in the Thomas Fermi atom. The goal here is to calculate this function f of r. And also, if you take these examples here in aqueous solution, for example, sodium chloride, you have positive and negative ions in solution. And there is no preference for either for positive or negative. So you have to make a statistical, you have to adopt a statistical point of view. Initially, we are going to start with positive charge, make the treatment for positive charge, and then by analogy, the result will be the same for negative charge, just change the sign. So we are going to treat initially only positive charge by discussing this ionic atmosphere by solving Poisson equation. The solution of Poisson equation has to be found. And we start with the basic electromagnetism. Electrical field relation is the gradient of potential, and the divergence of electric field is charge density over permittivity of the medium. And from that you get the Poisson equation, which is this equation, partial differential equation that you have to solve. We have to solve. Therefore, the first step to solve it is to calculate the charge density. It's the density of a charge, and this Z here, taking account if it's +1 or +2 and so on. And you give the Boltzmann factor for this energy, and the beta is 1 over kT, K Boltzmann factor. So this is the Boltzmann factor with density with an effective charge. This is the charge density. But since I'm considering high temperatures, I can make a Taylor expansion, and at this point I'm going to use the charge neutrality that I have talked before. The amount of charge is conserved, so the first term here is 0, and we end up with this expression. Substituting back this charge density on Poisson equation, we get this expression, where we have defined kappa as this quantity here. The solution of 51.4 is well known in this form. It's a exponential plus and minus. Actually, this Poisson equation, you can transform it, although it's a partial differential equation. If you make this substitution, you get just a second order derivative of this function here. It's a very simple transformation, and you are going to end up with this solution. But the solution has to be bound at large distance, so it cannot explode. Therefore, consequently, you have to make B equals 0. That's the final solution of Poisson equation for a proton surrounded by electron, by this charge density around a point. See the charge density around this point, interacting electron and proton. The next step is to calculate this constant A, and you just have to make this integral. The whole charge inside the volume must be equal to the negative charge inside this volume, this atmosphere. The whole charge is equal to the total atmosphere, ionic atmosphere charge. So you integrate this. You can integrate from 0 to infinity, and it's a very simple integral like that, this one. And if you equal the two terms, you get AK, which is this one. So you get this expression, the final expression for the Debye-Hückel approximation. for the Poisson solution actually, under this charge density that we have assumed before. For this charge density, we get this solution. But here we have not considered the size of the particles. We integrate from 0 to infinity. If you consider the size, this expression has to be changed to this one, as we are going to see in problem 1 later on this chapter. To proceed with our analysis of the Debye-Hückel theory, we have to quantify two quantities. One is the ionic strength that already appeared here on the proof of the potential under this cloud. This quantity here is related to the ionic strength, and the other one is the Debye radius, which is related to kappa. So we are going to quantify now these two quantities. First, the ionic strength, which is quite straightforward to calculate. Z is, as I said before, is how many ions of that kind you have in solution, and M is the concentration, molality. For example, let's take our three prototype systems. For sodium chloride, for example, which is 1 by 1, Z1 equals 1, Z2 equals 1. And you just have to calculate that. Ionic strength for an electrolyte of the form 1 by 1 is M. Ionic strength for electrolyte of the type 1, 2 equals 1 squared, 2 squared, 3M, and so on. For magnesium or copper sulfate, one of the two, you get 4M. We have now to estimate the Debye radius. And from the Poisson solution, we had this solution before for the potential. You can define a radius Rd, the Debye radius, which is equal to 1 over kappa. So kappa is the exponential, and therefore, then the Debye radius will give us an idea of the range of this potential. If kappa is small, Debye radius is large, and the ionic atmosphere will be bigger than if the Debye radius is small. Since for small Debye radius, you have large kappa, and consequently a very short ionic atmosphere. Let's put some numbers then to see how this quantity is in solution. Debye radius equals to that. I put some numbers, and you got that 3.04 ionic strength to the minus half, this quantity in angstrom. If you want, you can use the octave code, which is very simple, and you need only to put here the ionic strength that we have calculated and estimated before. So let's make a table of Debye radius for against at room temperature against concentration. You see, for a small concentration, for dilute solution, you see you have very large Debye radius. So in this region here, the Debye radius is going to be very large. And consequently, if the Debye radius is very large, kappa is going to be small, and the range of the potential is going to be large again. Well, since the Debye radius is large for dilute solution, which means kappa is very small, we can make an expansion of this exponential term, arriving at two terms for the potential. One is, you can see, is the original potential due to a point charge. And this term here is a consequence of the shielding. Now, from chemical potential theory, we know that the whole potential, chemical potential, is an internal one and an external. And this potential here, it acts like an external potential. And therefore, it's like an extra energy, excess energy. And you can make it equal to the Gibbs excess energy, which is RT log of gamma. But this is for one charge. If I add more charges, as I said, you get this potential actually. The same reason can be applied to the negative charge, because positive charge are surrounded by negative charge, and negative charge is surrounded by positive charges. So you get this both expression 16, which are activity coefficient for positive charge and the activity coefficient for negative charge. It is not possible to measure individual activity coefficients. Therefore, we have to deal with a mean activity coefficient, and which is defined by expression 20. You have a reaction like that, and you develop things you know from thermodynamics, basic thermodynamics. I'm not going to go into the details. It's very simple steps. So with this definition of the mean activity coefficient, average coefficient, we can proceed and calculate the mean activity coefficient, taking the logarithm of this expression, and you arrive using again charge conservation. It's very simple. Here the steps, we arrive at equation 24. Next step now is to put some numbers on equation 24. To get the final expression for gamma, the mean activity coefficient, you have to put some numbers here. This theoretical expression can be easily modified to that. And if you put the numbers, you get 1,171. Or you can use the octave code, which is the same. You get the same result, of course. I summarized this chapter in 2 tables and 1 graph. The first table is this one, which I put the prototype system, the ionic strength, the Debye radius, and the mean gamma, logarithm of mean gamma, and the gamma itself. So it's very simple expression, and as you're going to be seeing, as we are going to see, give very good results for diluted solution. The comparison with experimental data, either in a table or in a graph, are on this table and on these graphical results. Again, you can use the simple code to generate this table. Experimental results are the second ones, and they were taken from the handbook and the book by Latimer. Thank you very much. There are 3 problems that I ask at the end of this chapter. One is to reproduce the table of the Debye radius. It's very simple. We have already discussed it. You just have to run that code and verify the table. And the same for table 51.3, which are the table with the theoretical gamma, the theoretical activity coefficients by the Debye-Hückel approximation. Again, you just have to run the code that I give there. And the last chapter, third problem, is to recalculate the constant on the Poisson solution, but now taking into account the size of the particles. It's very simple. The integral is well known, it's simple. And you arrive at this expression. The important thing here is this expression for the potential will give another gamma function, which is given by that. A prime we had already defined before, the same constant as before. And the b prime is a new constant, but this b prime depends on the size of the particle, on A. And therefore, this expression, although it can be more precise, even for more concentrated solutions, it's not very appropriate, because it will depend on the particle, the property of the particle, the size of the particle. We are not going to use it here, instead using only the expression for b prime equals 0. Thank you very much.